Today's webinar will be given by myself, Hannah Blacknell. I am the application scientist here at Palintest. This webinar will take you through an explanation of accuracy and precision and their significance when it comes to water testing. I'll explain how to ensure that your data is reliable and reproducible, and how to ensure that you're making the right decision about water management, whether you're using colorimetric or sensor methods to analyse your water chemistry. The first question is, what is accuracy? So the official definition of accuracy is the degree of closeness of a measured value or calculated value to its actual true value. So let's step away from water management first and into sports. So let's think about archery. You stand however far away from the target and you aim for the bullseye. And if you are excellent at archery, you will hit it. You hit exactly what you are aiming for. If you are pretty good at archery, you will get near to the bullseye, perhaps the edge of the yellow or part of the red. And if you are terrible, then you might not even hit the target. Now, what we can say though, is that even if you're not very good, if you keep shooting your arrows at the target, you will likely get some of your arrows closer to the bullseye than that first one that you aimed. That's to say that as you practice, you will get better at archery. So if we move back from sports to the day job and water testing. So imagine a target. The bullseye is the true value, which is shown here by the green cross. If, for example, you are making up a standard 1 milligram per litre solution of free chlorine, I know that the true value is 1 milligram per litre because I made up the standard. And then I can do my 6 repeat measurements and see what the average or mean of the data is, and compare this with what I know the true value to be, which is 1 milligram per litre. And this will give me an idea of how accurate my data is and how accurate my test is. So if all the results come out close to 1 milligram per litre, then you're close to the true value, and we would describe the results as being accurate. The closer you are when you take the average of the data determines how accurate your data is. And so there's an example of high accuracy. All the orange crosses are buzzing around the green cross. An example of low accuracy, where all the points are quite far away from the green cross, is shown here. Okay, so we've done accuracy. We want to ensure that the data is accurate, but also that it is precise. So the definition of precision is the degree to which further measurements or calculations show the same or similar results. So if we use the target graphic again, here is the true value in the center. Now the precision does not take into account that true value. It simply measures how close the repeat measurements are to each other. So our first example, all the orange crosses are clustered out on the bottom ring. This data shows high precision because it doesn't matter that the data is far away from the green cross, just that all the data points are close to each other. On this next one, the data is quite spread out. See, there are significant gaps between each of the orange crosses, and so this data represents low precision. But what about the accuracy for these two? So the first one is low accuracy. The average of the oranges will be far away from the green. With the second one, it's more difficult to see. Some are close to the green, some are further away. And with accuracy, it's the average of the data that's important. So if we imagine where the average might be, represented by this yellow cross, it's quite close to the green relative to the entire target, but it all depends on what you're testing as to whether this is suitable. So if you're testing something where the actions are quite serious, this could be a water supply being shut off, a factory closed, a set of products being scrapped, then this degree of accuracy may not be enough for your process. But if you were testing alkalinity of your pool and checking it remains within between 80 to 200 milligrams per litre, then this accuracy might be enough. So I've jumped on the fence and called it okay accuracy, all depending on where you're testing and what you're testing. Thinking about two other words, they're really closely linked to the two definitions that we've already discussed, and that is reliable and reproducible. So as well as accuracy and precision, there are two other words that are thrown around a lot in the water testing industry. You want data that is reliable and reproducible, but what do these mean? So reliable data generally means that you can trust it, But really the only way to know whether you can trust it is to see if you can do it again. Well, that's reproducibility. So they both mean very similar things. Can I trust the data? Did I do it correctly? And could somebody else do it again? Sometimes it's easier to think of reliability as being similar to accuracy and reproducibility being similar to precision. So the eagle-eyed amongst you might have noticed that the promo picture of me that keeps popping up on the blue slides is of me wearing a funny hat, and that's the day that I collected my PhD in chemistry. So one of the key things in chemistry research particularly, but in science in general, is that you need to be reliable in what you say. We need to know that your data is right, but also that you've drawn the right conclusion from your data. So when you're testing your wastewater outlet, for example, and you get a result that means you need to act to mitigate the associated risks, then you want to be sure that the action you are taking is going to solve the issue, but also that the issue is there. So I always work by the rule that if you get a result you weren't expecting, repeat the test. If the same thing happens again, then you should act. Now, based on what I've said just there, I want to be able to apply that knowledge into real life situations that we encounter in the water industry. Understanding precision and accuracy clearly can help to ensure that we make the right decisions when it comes to adjusting the treatment of water or interpreting the results of our water testing. So the first decision is what kind of method is best for you. There's such a wide range of testing methods for analysing water in fields that choosing the right one for you can be tough, as not all of the methods are created equal. The general decision is between how easy it is to use and how reliable and accurate the data you get is, and which is most suitable for the application in which you are working. So many of you will have seen this matrix previously in some of my other webinars. Here we have a matrix which has axis that runs from easy to do at the bottom up to hard to do at the top. And then we have left to right, we have the potential accuracy. And this is a measure of the quality of the data that you can achieve. So easy to do visual tests like test strips and drop-down kits are generally quick and can be done by unskilled users, but the quality of these results is relatively low, and so those methods sit down here. With lab methods such as titrations, you would get much more accurate results, but these require a highly skilled operator and generally take much longer to do. So they sit up at the top. The alternative to these are instrument methods. So these offer higher accuracy and precision than the visual techniques, with a method that a trained user will be easily able to carry out. Here at Palintest, we offer a variety of photometers, and these sit here and offer higher accuracy with an easier method than lab methods. And we also offer sensor methods on the Chemio platform, which offer very high accuracy with a method that is on par with the test strip for simplicity. So in short, if you're making water management decisions, you need to be sure that the method you are using is going to give you the quality of results that you need to make the right decisions. So the real reason we're all here is how can you apply the understanding of accuracy, precision, reliability, and reproducibility to the water industry. When dealing with water testing, there are some things that make our lives a bit more tricky. The first is that we don't always know the true value. We are testing an unknown sample and trying to get a reading, as opposed to testing a known standard like you would perhaps in a quality control process or something similar. This means we can't just look at the data and know if it's accurate or not. Another, water is never homogeneous. What this means is that no two samples of water should be the same. Pocahontas got it right when she said you can't step in the same river twice. The water is always changing, always flowing. See, who knew there would be a Disney reference here in this technical webinar? This non-homogeneity happens when the water is flowing and new water with new levels of different parameters is being brought in, or the water is going through pipe work, getting air introduced to it, contamination, etc. This can also happen when the water is still. When there is no flow in or out, there can still be settling of certain things to the bottom, or sunlight could destroy some molecule at the top and create something new. There could be temperature changes. I don't think it's possible on Earth to get a truly still bit of water where there is no change at all. Perhaps in a sterile container full of sterile water kept in the dark in a fridge that's never opened. But who's going to do that? So anyway, the point is that we can pretty safely say that no two water samples you take will be identical. What this, of course, means is that when you're doing your testing, you'll never get identical results every time. So how do we tackle this issue? The best way to do this is to always sample from the same point and at around the same time each day. Both of these actions will help to reduce the variability that you see in your data. But the main way of ensuring that you get good data is one I've mentioned before, my favorite one, which is to take repeat measurements. It's an easy way to identify an issue as being due to a mistake in the method or sampling rather than an issue that needs to be rectified. So let's think about some real life testing. So for this example, let's think about a pool in a leisure complex. So first, selecting the method. It's a commercial setting, so bather health and happiness is important. So we'd be wanting to use an instrument method, not a visual method, to ensure we're getting the best bather experience. If we're testing disinfectant chlorine levels, for example, the pool must maintain a certain level of residual chlorine in order to keep the bugs away and keep the water safe and clean for bathers. If you test the water and the residual chlorine is too low, then the pool can't be opened to the public until the level is correct. If the chlorine levels are too high, then you'll get strong smell, bathers will get itchy eyes, and many people will start sneezing, bringing some more nasties into the water. So it's a balancing act between not overdosing and not underdosing, but getting everything just right. Making smart decisions on dosage has significant cost benefits, but also means an improved bather experience too. So in a pool, there are deep bits, shallow bits, filters and pumps and jets. To get reliable results, we want to make sure we are testing the same place, not near a jet or a filter, not in the shallow parts or at the steps. We also don't want to test the top part of the water because you can get different reactions in the water at the surface to in the main body. So generally the advice is to test from elbow deep. And if the result is not as you were expecting, quickly run a second or third test to make sure that the result is true and to give you an average reading to work from. Adjusting dosage based on the average reading will help to make sure that you make the most informed decision about the remedial action required. What about a totally different setting? A fresh produce washing line. Let's start with salads. So salad leaves come in all muddy and full of caterpillars and the like from the fields. The leaves are cut off the stalks or stems and they are thrown into the wash lines. The wash water is recycled and needs to be disinfected to make sure there is no cross-contamination. So again, the first thing we need to think about is what method to use. Now, the biggest no-no for food processing lines is glassware. If a tube were to break and get into the line, the whole batch of product would have to be binned. So we want to stay away from glassware, so we could use a photometer with plastic tubes, a simple visual method like a test strip or drop count kit, or we could use a sensor method. The choice could be down to how skilled your workforce are and how much time they have available to do the test. But equally, it could be down to the quality of the data you require. How tight is your quality assurance allowable disinfectant levels? Or what are your particular rules for use of chemical reagents near the produce lines? Regardless of what decision you make in which method to use, what is really important is that you collect good data. And the best way to do that is to minimize the variables and keep doing repeat measurements. The average will mean you are less likely to have freak results. If you do have them, you can identify them. Your results will be reliable and reproducible as you will have done them multiple times. So what we want to do, regardless of the application you're working in, is to ensure that the data you get is good data. It is reliable, reproducible, accurate and precise and good. And therefore you can be safe in the knowledge that from that data you can draw the right conclusions and carry out the right action. Adjust the correct chemical by the correct dosage and act to reduce a risk at the right time. What is a really important take-home message from this webinar is that both accuracy and precision are important. You need to understand your applications. How good is good enough for your application? And then how can you ensure that you're making the right conclusions from your data? That will mean you can manage your water better.